Right, so we're driving around the CERN, what do you call this? The CERN
site.
The CERN site.
And we yes, so we are approaching now the computing center of CERN.
Yeah.
There is one of the buildings over there. Inside there is the large computing center where there are several thousand PCs, mass storage devices and our server infrastructure.
Alright.
The size of the center is mainly limited by the cooling capacity, because when you have many computers in one room, you need to have a certain amount of cooling power.
Alright.
So let's see if we still manage to enter.
We'll try.
Okay.
So all this is just coolers and computers?
Well, there are also offices.
Right.
But,
yeah.
So we are going now to the computing center. Here there is the main office space and the IT auditorium. On that side is itself the center itself, and there are some offices where various developments are being performed.
So these offices have been built quite a while ago, no?
Yes. The whole CERN site the buildings are not new, but they are being used again and again.
Yeah.
But basically the full computing center internally has been refurbished in the last years.
In the last years?
Yes, because
to prepare for Atlas?
to prepare the new experiments and the operation at LHC. So there will be some noise inside.
Yeah. So we're entering, what are we entering? Can you describe?
That's the computing center where we have all the server infrastructure and the computing which is necessary to operate the LHC experiments. Basically, when we look around, you can see here some more classical structure. You can see these boxes here are normal PCs which are just put on racks to provide computing power. We can go over there. Here we can see more modern devices based on blades. So this is things like that. So you have here single computers which are inserted into racks, and here it continues like that. Here so we are providing our computing structure with a large number of blades processors. Basically the whole structure is designed to do the cooling. On one side cold air is coming out of the ventilation, and on the other side the hot air is coming out.
Can we see closer how it works?
So you can see here we have the cool air coming out of the ventilation.
Down there?
Down there, yes. So it's blowing up a cool stream of air. It's then sucked into the racks, and on the other side hot air is coming out. So inside it's here.
It's hot. So is that gigabit internet or?
Typically our networking on the level of PCs is fast internet. So I would think, from what I see, this is fast internet, because basically you don't need for most of the application. It's sufficient on the level of the individual PC to have fast internet. It's then concentrated on some level, typically on onto a concentrator, and then you go up with gigabit internet traffic. Here over there you can see the CERN internet exchange point. Here the CERN is connected to the worldwide internet, and we have connection going up into all places. I'm sorry.
Oh, okay.
On the other side over there. So here we have the internet backbone. We can have a look at it.
The Ethernet what?
The backbone to the CERN intranet, and the connection to the external internet.
Alright.
So these are basically switches, and here you see mainly these thin cables. This is gigabit internet. So gigabit internet, Ethernet. So these are optical phasers, optical cables, which are used to transfer the data to CERN and to distribute the data all around CERN.
So it takes the data from the experiments? Is that on here? It comes in?
Everything comes in. The data from the experiment will arrive here and will be then distributed to these other computers.
So only this is enough for the whole of Atlas?
This is enough for the experiments. But these are routers with high capacities inside here.
Very special routers, or
yes,
is on the market already?
Well, these are things which you can. This is all computing is based on technology which you can buy. So there's no need to specially develop.
Okay.
Things.
There's no special. Kisco didn't do some special routers for.
No. This is something which you can buy. So there are other big consumers of switches like telephone or television.
Because what I understood is that the Atlas is pushing out so much data, is amazing. You know, it's the biggest data ever.
Yes,
or something.
but the technology, the computing technology, when you follow it from the experiments, very close to the detector, you have a lot of custom-built stuff. But the more, very soon, already when you are up from upstairs above the experiment, you have commodity hardware.
All right.
This is due to the fast development in computing.
Right.
We do most of the things with commodity hardware because commodity hardware has the advantage of being cheap, being easily replaceable after some years. While when you build something yourself for a specific purpose, you probably have to live with that for the next 10 years. If you buy something, you will probably throw it away after 2 or 3 years or replace it by something newer.
You can just replace easily.
Yes, but so basically the moment you have standard technology, it's much better. For the computing, it's very essential because there is Moore's law, and it predicts that within 18 months you have a doubling of the computing power for the same price. So, but this is actually only for stuff which you can buy at a shop, shop for consumer hardware. If you buy something very fancy with special electronics, nobody will. You have to buy it again after 2 years, and it will be much more expensive. But when you buy standard equipment.
So here is standard equipment.
Is
expensive but standard.
Expensive but standard equipment. Particularly the progress in computing was so high that today we don't have any supercomputers here anymore. Our computing needs are much better served with a large set of standard computing equipment than to buy. In earlier times we had here Suns and Cray supercomputers, but they are not really suited for our purpose.
Did you say Suns? Like Sun, the computer.
But we had for some time ago we had a very nice Cray here. And the Cray is one of the big supercomputer.
The Cray, okay. Some time ago, like.
Cray, yes. Cray they were one of the biggest supercomputer manufacturers. They were very nice to look at, and were also very good. But today it is much better to have a large number of PCs to look at. We have a second store here. This is just one half of the equipment. So there's a second store where we see a large number of compute servers and also tape storage systems which we use to store our data.
That's what you're going to use, the tapes? So how about the bandwidth? Can you say something about bandwidth in this area here?
It's typically what is well, I cannot say too much, but CERN basically is connected with 10 gigabit Ethernet connections to the large computing centers, to 10 large computing centers around the world. So there is a kind of a backbone which has a very high capacity. During the operation of the experiment, we will export data out of CERN at a rate of about 1 to 2 gigabit per second on a continuous basis.
To one point at a time?
No.
To all the points?
To a 10 computing center around the world, the so-called Tier 1 computing center.
Do you use like peer-to-peer?
No.
No?
No, we have dedicated networks, so there is no. The peer-to-peer allows you to overcome problems of low connectivity. We have very high connectivity, so we can put into our. The problem is rather how can we get 1 gigabit per second to the switch. The problem is not the capacity. The problem is the structure behind. What can give me such an amount of data in a constant rate to my switch. This is the problem.
So the switch is here?
This switch is this switch are here, yes.
So those switches can do up to 10 gigabits, but they're doing...
There is no... the problem is not the bandwidth, the problem is how to get sense-making data. One has to compare, we are sending data like every 10 seconds the contents of a DVD.
Can you show just one of the special hardwares that needs to be like the one that really is crucial?
This I cannot really show.
Yeah?
We see here, this is for example a typical gigabit switch, as we can see, and you can see here various optical fibers coming in, being connected in various ways. You can see here this is gigabit, and this is here is fast internet connections.
Right.
So this is kind of, but I'm not really a switch expert, I have to say.
So where are we going now?
So we're going down.
Down?
There is another floor where we have more equipment.
Right. So this is just all these computers are just part of it's kind of the same as all the other countries. You also have the same kind of computer.
Yes, basically at CERN we will have about 10 to 20% of the computing capacity necessary to analyze the data of LHC. To analyze LHC data, we will need about 100,000 of today's PCs.
100,000.
We have here at this today we have about 2,500 here at CERN.
Yeah, there will be more.
They have a second floor where there will be more.
Yeah, but did you say you need 10 to 20%? It's like 20,000, no?
Yes.
So right now you only have 2,000?
Yes.
So you are going to buy a lot?
But basically we have not yet spent our money to buy computers because the experiment will only really start end of the year, and afterwards we will have a large increase of the need of computing capacity.
So within the next few months you're going to buy 8,000 computers or 18,000 computers?
Well, evidently there is some spending profile for the next years to get this. I cannot tell you details of how many computers are going to be bought.
But it's not really has to be here. It can be any other place in the world. Is that the point?
In all places in the world, they have similar plans to upgrade the computing centers in the next years. So it goes on here like that. Here there are more computers. Up there is more the server infrastructure. And it's a bit a traveling history because as you can see here we have only these boxes, and these boxes are older than the blades which we are buying today. So it will be in some time we will replace again these boxes here by newer systems.
Blades, does that have anything to do with the IBM cell processor?
Yes. No, not really. No? We are not using IBM cell processors. Basically we are using here mainly Intel, maybe some AMD processors.
Some AMD, but the cell is not. You don't know if you're going to use it. Supposedly it's faster, no?
Supposedly it needs special programming techniques. At this point, we are interested naturally in the systems which are here are typically dual processors. So now probably the world is moving on that mainline computing into the power into dual processors and quad processors, but the cells, I'm not sure if the numerical floating point capacity of these computers is...
What did you say?
If the floating...
you're not sure if they do that kind of...
The floating for cells, I would suppose they have a lot of spec-ins, but I don't know if they are really suited for scientific computing.
Right. So mostly it's Intel?
Mostly it's Intel, yes.
Right.
But this is just by chance, it could also be AMD. You can see here our storage subsystems, and most of the data is stored on cassettes inside here.
Sorry.
And you can see inside here a robot which is transporting, which is accessing data which is stored on tapes.
Nice. So there's a robot going around taking the tapes?
Taking the tapes and putting it into the drive. So this is basically we have large disk storage, but at some point data is still going to tape, because tape is a very good storage media. One tape here has a capacity today of 500 gigabytes, which is the equivalent of 50 DVDs or something like that.
So
And
tapes are cheaper than using hard drives, or
tapes are cheaper than using hard drives and using.
they use less power because they turn off when you don't use them.
That's no, but yes, but evidently you have to mount the tape when you want to use the data. So we have discs as a cache before the system. So we don't access the tapes directly. If we need some data, we take the file from the tape, we put it on the disk, and we use it then from the disk.
So how long time does it? It takes a few seconds, no, for to get the tape and.
Yes, if you want to request a random file which is on a tape, it would take you, depending, can take also several minutes until the file is available.
Because if it's busy, you have to wait in queue.
Yes, yes.
Yeah.
But evidently this is then a method that the experiments will sort the data according to the needs. So data which is less used will disappear
Will go onto tape.
Will go onto tape. Other tapes will be also on tape for security, but the data will be available on disk for analysis.
Is that where you do the backup, maybe?
Not only the backup. I mean, there's a lot of. Well, it's also for the backup, but in case of the data storage, you don't speak of backup, because it is not something which you want to restore. It's something you use data for some time and then you keep it on, you archive it on these cassettes, and maybe you need it in some time, maybe not.
Is that system something that's used all over the world, or?
Yes, these are systems which we have several of them here. Here is the older one. This is older one which were round silos. Today they get more bulk.
So those are tapes? This is normal tapes?
These are such tapes. Over there is we have a
500 gigabyte for one.
These are, well, some of them have 500 gigabytes. I don't think this one. I think these are look inside here. No, this looks like this looks like it's not an operation. There's a camera close to the robot, and we can see what the robot is doing. So he's finding some cassette, taking a cassette out and moving it into another place.
Moving it to the reader or something?
Yes, exactly.
Yeah. And the writer also.
But there's a tape station where tapes can be written or...
How many places can it read and write? Just one place, or?
No, there's a number of them. I don't know the details. But there's a number of reading and writing places. We can go on.
So how many computers are down here?
There are, in total we have currently about 2,500. I don't know, down and up. I don't know how many are really, how many are details. You can see here another tape drive. So you can see this is a lot of things are these tapes where we are storing this data. So this is a big part of the operation here. And it's also expensive because such robots are not cheap.
Such bugs or what? Did you say?
These robots are not cheap.
Not cheap.
PCs are cheap.
Yeah.
But this robot is...
So this robot contains more than the IBM one, or?
It's a newer model, IBM.
Yeah.
So but you can see here the capacity of various media.
Yeah.
This is what was used in the times of lab with 20 gigabytes per cassette. And today you have media which goes up to 500 gigabytes. And you have read rates of about 120 megabytes per second. So
is that better than a hard disk drive, or hard disk drive is actually faster?
No. A hard disk drive is faster.
Alright.
But a hard disk drive will allow you also random access. On the tape, you don't have random access. The best is you dump the content of it. If you want to use it,
you have to wait for it to read and all that.
Yes. So it's very good and cheap. It's much cheaper. I would assume it's something like 10 Swiss francs.
10 Swiss francs for 500 gigabytes.
Yes.
That's cheap.
Yes.
So it's kind of like a DV tape for the camera, no?
Yes, exactly, exactly. But it will, the drive will be very expensive.
The drive.
Because the thing where you can read that will be very expensive. This will cost it will cost as much as a car.
As a car?
Yes.
All right. So all those.
And these are CPU servers of various times. Here over there.
So it looks normal then. It's been for a few years here, or?
It's been since some time. I would think 4 or 5 years.
4 or 5 years, okay. So
but the limiting aspect is not the size of the box. The limiting aspect is the heat, and it's the same if there are big or small boxes. You can see here there are again some newer infrastructure. In that particular case, I think
it's been for a few years here, or?
It's been since some time. I would think 4 or 5 years.
4 or 5 years, okay. So
but the limiting aspect is not the size of the box. The limiting aspect is the heat, and it's the same if there are big or small boxes. You can see here there are again some newer infrastructure. In that particular case, I think it's disk storage which we have here.
The air circulation is always good in here for workers.
The noise is always like that. Yes, this is the climber.
I mean the noise, but how about the air and the oxygen?
Yeah, no, but there's a need to have, because of the heat which is generated. There's a need. There's large cooling equipment in the house to remove all the heat which is generated here.
All right. So when Intel makes a newer chips that does less heat, is good. It's good for
naturally, yes.
These places.
We are more limited, but the problem is the heating capacity you cannot increase forever. This costs a lot of money to have new cooling equipment. So if you have computers which produce less heat, it saves you a lot of money because you can put more CPUs in the same room.
So these, even though they're 4 or 5 years old, you don't need to change them for the experiments?
They are going, we are constantly renewing these things.
Right.
I mean, it's not that we throw them immediately away, but after sometimes PCs are getting obsolete.
And what do you do with them when they're obsolete? They might be used for something else, or it just goes...
Typically after some years a PC has little value.
It goes to recycling or something?
Supposedly, yes. Yes. Typically it has little value. I mean, this is like, evidently when you are at home, but typically we use our PCs quite long because they are also, I mean, today, I mean...
there it looks like it's old ones, or...
Yes, but this is... But whatever the
up there is just an old one.
This is an old terminal switch. So there is a lot where the equipment accumulates over the time, but there is a constant. The main problem is also that you have to have service contracts, because I mean evidently you will have, when you have so many PCs, many things will break. I mean, this is standard equipment, so it will break up. So you will have probably one PC breaking down per day, and you have to change power supplies, hard disks, and so on. So you need also to have some maintenance contracts for such things, which will be the more expensive thing.
All right.
Okay, so we go now out because outside there's less noise.
Less noise, yeah. We can talk about. Maybe we can talk about the grid a little bit.
Yes. So, but let's find a place to sit down because I have some.
Okay, so what are you showing?
So this application shows the status of the grid right now in that moment, and you can see various sites which are interconnected by the grids, and on the grid we can show, for example, this is England, and you can see here various sites in England. The green, so a circle is showing a site, green are jobs which are being currently executed, red or magenta are rather are jobs which are waiting to be executed on that site. So we can, for example, check which laboratory is here. This we are in Sheffield, and we see Sheffield is a very small site. There are 7 jobs currently running, so and 4 scheduled. So there are probably not too many CPUs available for us. Here we have a larger site. Here we are in Manchester, And here we have about 200 jobs running and 35 waiting to be executed. You can see here in this display sometimes lines, and these lines indicate jobs which are being submitted or results which are being returned. So a magenta line indicates that from somewhere in the world somebody is requesting some work to be done on the other side, and the yellow lines indicate that the results are being returned to the person who is sending it. And you can see here also sometimes red lines, luckily not now. These are cases in case the calculation has failed and one couldn't return a positive result. So you can see that we have sites in various countries. In various countries, here we have Europe. You can see that we even have in the middle of Africa a site, which I unluckily don't know exactly in which country. We have some in Tunisia, but if we go on, we can see here the Mediterranean. There are some sites in Israel, Cyprus, Turkey. That's probably...
So when it's blinking, kind of, there's activity, right?
There's activity, yes. You can see here, for example, this site. Well, this site, there are currently jobs only scheduled. This is, for example, in Krakow. No, this is Kharkov. Sorry, this is not Krakow.
Yeah.
This is in... Interesting question, which country? I'm not 100% sure. At this site, 9 jobs are waiting to be executed somewhere in...
Maybe it's in Kazakhstan?
Kazakhstan, probably, maybe. Yes. Georgia should be down here, shouldn't it? I'm not... Okay. So we can see here various... And all these sites...
So there's something going on the line there, or yellow?
So the yellow thing, this means the result is being returned.
Right.
So you can see here, this site has just finished one result, and this was requested from CERN, and the result
CERN is in the middle.
CERN is this thing here, yes.
Right.
So this is the CERN site, and you can see on CERN we have a number of... So this indicates some element of the grid infrastructure, which is not so important, but we can see that at CERN we currently run 4,700 jobs on part of... So we at CERN we run currently 1,200, while we have some infrastructure which submits the jobs, which are called resource brokers, and on that we have currently 4,700 jobs. In total, currently the grid is currently running 12,000 jobs.
12,000 jobs.
On in total about 200 sites, which have about, in total should have about 20,000 CPUs. Conceptually available. Not all of them is permanently available.
So a job is one CPU?
A job typically takes one CPU.
Or a dual core maybe?
Typically one slot. A dual core machine would have 2 slots. So it's CPUs.
Just a CPU, so it's just...
So there are about 12,500 CPUs are being kept busy by our activity currently.
Each CPU is kind of at least 2 gigahertz or something?
This is depending on the country and the site. Particularly on, as I was telling, we have the computers are typically older, but today's computer you buy today naturally are faster than the one which you're buying some time ago, but typically you would expect at least to have a gigahertz PC which has something like 2 GB of RAM for each slot available.
Which slot? So right now it's 12,500, but this is just for testing, or
this is just for testing. Yes. Well, and for doing first initial analysis, doing initial simulation. In total, we need to have to go up to about 100,000.
100,000. So right now it's 12,000.
So we are still in the beginning.
All right. So do you have to use what do you call them, institutes, or those places where there's big parks? You cannot just use personal computers?
They are personal computers as they are down there, but they are not all. It's not possible to have so many computers available at CERN. You will not. You can. It's possible to have at CERN several thousand computers, maybe 10,000 maximum, but it's definitely not possible to have 100,000 computers at CERN. Therefore, it's necessary to use computing power which is available in various institutes or other large institutions around the world.
No place in the world has 100,000 CPUs, or
this I would not say completely, but for in the scientific area, it is it's a very large number. Evidently, there are companies like Google or oil companies who can afford a lot.
NASA maybe?
NASA, probably, but I don't know. I would think that they're rather in the scientific ballpark. Where such a company can afford to buy, if they need 10,000 PCs, and they are all the same, and it's we have a much more homogeneous, a much more inhomogeneous system. As you were seeing already down there, we have computers which have different ages and so on, because we have a need to do a very efficient management of our resources, not to be more efficient. In the end, the grid is a lot about sharing resources. Evidently, when some of my colleagues, I'm Austrian, some of my colleagues in Vienna, when they buy some computer, they will use them for their work, but when they are not using them for their work, they can contribute with the CPU resources for the overall experiment. And we from CERN can send jobs to Vienna, and they will use the computers while the people in my colleagues are sleeping or having
could you use private citizens' computers? Like there's some other group,
conceptually we can do that, but this is not for the scientific computing we have in mind. It's not practical. We do data intensive computing, therefore we need computers which have access to large amount of data. These
private
projects which do these private grids, they are typically computing intensive. They use a lot of CPU and have little data exchange, so they don't read gigabyte of data over the network. For example, but they do some calculation. They find some. They do, for example, it depends very much on the application. When you do a data intensive, then you need access to storage resources, and this you simply don't have
for example,
at somebody's home. The original is SETI at home. There you get one piece of data, and on that the computer is then busy for a day.
Alright, that's a piece of data. Do you know how big? It's just a small one.
It's a small piece of data. It is not, while we are trying to reach, so the data which we are analyzing is being condensed and filtered, but even in its final form it will be about 150 terabytes for 1 year. So a physicist who wants to do analysis to analyze the data of 1 year will have to process 150 terabyte, which means he has to do 150 terabyte I/O. This cannot be done with an infrastructure which is based on personal computers which are connected.
So each of those computers here have big hard drives, or?
No, you have the computer has some hard drive, but we have the grid is based on storage element and computing elements. So basically, you have on a side you have some infrastructure which is for the disks, and they are connected by switches and network to the CPU resources.
All right. So for example, IBM also has a grid, right? But they also use, I guess, smaller.
No, IBM has. I don't know.
IBM
probably has many. IBM has also a grid. So IBM also has invested in grid technologies. I don't know how. This particular application for data-intensive computing is something which we do in this context of this EGEE project, which is not really a commercial thing. Right. Evidently, for different purposes, you need different types of grid as of today. The grid is not yet a uniform thing like the web.
But if you could get like tens of thousands of people with maybe 1 gigabyte each of this space, would that be helpful?
We couldn't run, I mean, to run our simulation program, for example, we need 2 gigabyte of RAM, and we need a PC for more than a day, uninterrupted.
More than a day uninterrupted, and 2 gigabyte RAM.
So it is not super practical.
Not many people have that.
It's not practical. There are some simulations you can do using less resources, but to simulate a detector like the Atlas detector, this is what I was describing about the resources which are necessary to simulate the Atlas detector. They don't fit very well. The second thing is to prepare that we need to install software first on a machine. So we need large software installation areas where we have to go regularly to update the software. So we have So we have about that's also not possible. So we need 2 gigabytes of software installation to be able to.
2 gigabytes. So it's a little bit complicated to try and involve the normal citizens.
Evidently, yes.
Evidently?
For this type of application, it is not really something which.
You cannot split it up somehow and.
Not really, because this is quite interconnected. This typical high energy physics simulation is. You have a very detailed knowledge of the whole detector, so you have to describe the full geometry of the detector, and you need basically. The nice thing is that each event is independent. You can split it in events, so you can, and this you can run on many CPUs in parallel. But you need at least this huge. Therefore, for example, we are not very well suited to use supercomputers. In supercomputers, there are other scientific domains, like, for example, also physics domains, like people who are doing quantum chromodynamics. They can profit from supercomputer architectures. We cannot profit a lot from supercomputer.
All right. So, do you think that the research with the grid and all that, the technology could that be used for normal people maybe in the future, where just as CERN invented the internet, you know?
Yes. Well, CERN has not invented the internet.
I mean, at CERN.
CERN has. I can show you maybe some. But I don't know. I have some presentation, which was given last year at the conference in Mumbai, where the application. So this is just some typical. So the idea is, what is the relation between the web and the grid? Originally, so just I can go and show you some if this is fine with you. I don't know if this is useful for your.
Okay, I'll just. So can we imagine the grid technology that is being developed for the CERN experiments? Can that be maybe translated to private use? For example, let's say a $100 laptop, which has a very slow CPU, and if you wanted to render some video or something like that, could you just send it to a grid somehow? Is that something?
This is probably This is not what we are. The problem will be that is not what we currently are focusing on.
Yeah.
We are currently focusing on making scientific grids where we are connecting large computing centers which provide the computing power. So this is depending on the type of application. This might be. The problem with grids is that you, contrary to Google or something or some web application, in a web application you allow the user only to do a very well-defined task. Basically, at Google you can basically search. You cannot use their computer for any other purpose. The grid has a different aim. The grid wants to provide you access to the resources somewhere else. Now, what I'm doing on the resource, I want that my program is executed on another resource. For that, you need to establish a trust relation between the person requesting something and the other side. If my job, as you were seeing, the grid is a completely international thing. There were sites in Africa, sites in the US. So basically, the grid allows some collaborator of my experiment in Atlas, independent of the country, to use resources in the US. So this might be even countries which don't have good relations.
Oh yeah, so maybe there's a physicist in some other country.
Yes.
Or they don't have to be in CERN. I mean.
Well, the point is the physicist will have to be member of the Atlas experiment, and Atlas is guaranteeing for its so the grid has a concept of virtual organization. So Atlas is guaranteeing that its users are doing reasonable things and that these users are identifiable. So in case the grid has a security infrastructure which is based on certificates. If I connect to another site and run my work there, they are able to identify me, and in case if I decide to use the computers somewhere for some illegal purpose, they would be able to localize me.
All right, so physicists they might propose some projects to do. and they get somehow chosen. They get some certain hours on the whole grid somehow.
Yes.
They get some processing.
So basically, the grid is made up. I mean, nothing is for free.
Yeah.
So to be able to use the grid, you have to get member of a virtual organization, and this virtual organization will do the resource negotiation for you, and then. So basically, for example, in my case, it's the Atlas experiment. I'm also with the Atlas experiment. The Atlas experiment has discussion with the various institutes, and these institutes contribute resources to Atlas, which they share via the grid. And I, as an Atlas member, am then able to use these resources available to Atlas.
All right.
But nevertheless, Atlas does not know what I'm individually doing. I could send a malicious program somewhere, and if they would spot that, the grid nevertheless provides security infrastructure to be able to identify who was doing that. So this requires some administrative overhead, evidently.
So you can kind of monitor who's doing good projects and who's maybe wasting some cycles.
But the wasting of cycle is not. The wasting of cycle is also a problem, but it's a lesser problem. I mean, it could be that this person decides to use the grid to distribute movies.
Oh yeah, illegal movies.
Well, whatever kind. I mean, it can become.
Because it's on the real internet. It's real IP addresses. It's not IP version 6.
No. This is all real. So basically, as I was telling you before, we have a capacity to send out data with a rate of a gigabyte per second. So in 10 seconds, we can send out a full movie on a DVD without re-encoding and other.
Actually,
other
if
things.
It's re-encoded, you can send nearly 2 movies a second.
Yes. So this would give, evidently, if some group would hijack that infrastructure, would give a fantastic backbone for distribution.
Oh yeah, of illegal stuff.
So this is not.
Is that one of the fastest backbones? Kind of.
Typically in autumn there is always a challenge who manages the fastest transfer, and CERN is typically participating with some laboratory in the US.
Oh yeah, that's the fastest transatlantic and stuff like that.
There's some internet speed record.
Oh, yeah.
But the problem is less the absolute speed. The problem, as I was saying, is how can one obtain a sustained rate which should go over weeks and months.
The ruler or something.
But you know, you have the robot with the tapes. So the data, somewhere the data is on disk, on tapes and so on, and it has to be brought to the network switch in an organized way. I mean, we have to send the data over the network, we have to make sense of the data before, we have to make sense of the data afterwards. So it's more an organizational problem. If we would send random data, we could fill up the bandwidth easily, but as a matter of fact, as we have to access storage systems and to be sure that we make sense of the things, it's difficult to keep up such a rate.
All right, so when Atlas is starting later this year, all the projects to use all the computer are already prepared, ready, and people know what they're going to do at what time, or
no, not
still
really,
have
not
to
really.
figure out?
We have still a lot of work in front of us. Right now we are working on the distributing of the data between the sites, because we have the infrastructure, we can do already some transfers, but we have to find ways how many replicas of data sets, for example, we want to keep. Yeah. I mean, evidently we have a lot of storage together, and we want to distribute our data on various sites, but we want to have also several replicas. So we don't want that. We want to have more than one copy of the data available.
You don't keep a copy here all the time?
No, we keep a copy here on the time, but we have to give the people the possibility to analyze it. We have to send the data to a place where the CPU resources are available.
Right.
So we send some data from CERN from here to a laboratory, and at that laboratory there are some free CPUs which allow physicists to analyze the data. But the question is, do we want to have one copy of the data out in the grid? Do we want to have 2 copies? Basically, we are working a quite complicated schema which takes into account that there are several countries involved and there are larger structures. So basically, we are sending out. It's kind of hierarchical data store. So we have all the data at CERN. We send copies to the big participating institutes, and from the big participating institutes again to smaller institutes.
All right.
So it's a complicated scheme which requires a lot of care being implemented.
Does it also depend on the results you get from the experiment, what you're going to research in? Or you can
the experiments are kind of general purpose experiments, but basically it depends also on the interest. For example, in a country you might be more interested on a certain side of data because physicists in that country want to look at some particular physics effects for which you need one set of data. In other countries you are interested in different data sets, so you have to do a lot of negotiation and discussion how to organize that.
Something I also kind of heard is that that's only like 1% or something of all the data that actually is used somehow, or is it less than that?
Well, the point is that we are doing a huge filtering. It's a huge filtering process. You
Down
might
at
have,
the Atlas.
In the whole chain. When you think, for example, it is sufficient if we want to discover this famous Higgs boson, which probably you have somebody talked about it. We have few events in a year. And this we have to filter out of all the collisions which we have. So just to show you,
few events in a year.
In a year, yes. So we have in 1 second, we have every 25 nanoseconds we have a collision. This gives you overall a frequency of 40 million collisions per second.
40 million collisions per second, and only a year are really interesting.
So we have to filter this data over many steps down to find these few events. So this doesn't mean that the other data is useless, but it's difficult, particularly, to find these few interesting events.
That sounds so. Is it for sure that you're going to figure out how to filter it?
This is what we are trying to convince ourselves that we can do since several years. But basically, yes, you can easily. You go down already in the first stage. You throw away a large amount of data which are so the problem is that you cannot generate a Higgs boson, for example, like that. You have it's a statistical process. It will appear only in very few events, and only in even less events it will be visible, because sometimes it will decay in a way which is not detectable by our detectors. So what we have is so in the first stages one is throwing events which don't have a certain characteristic and so on, and the first stage is not even leaving the cavern down, and there's a reduction from this 40 million events to about 100,000 per second. Then with 100,000 events per second we 10,000
for
events
sure.
per
In
second.
those 10,000, outside of those, they cannot be Higgs or something like that.
So if in case we have make a mistake in the first selection, where we go to 10, it's about 100,000. So all the other events are already gone. So out of these 40 million, we already throw away a large bunch, because we cannot even read it out.
You cannot even read it out.
But it stays in the detector. In the detector you have digital pipelines. The information stays stored in the digital pipelines, but we cannot read out 80 million events per second, 40 million events per second. We read out only 10,000. So
100,000.
100,000. So already we throw away lots of events because we simply don't read them out.
Why can you not read them out? Is it because the hardware is not available?
No, first they are not interesting.
They're not interesting for
They're
sure.
not interesting for physics, no.
All right.
No, because there are lots of the collisions will produce completely standard physics, which is already known. But only in rare cases these such special events are happening. It's a statistical process. That's
only
the whole reason.
A couple times a year.
Yes.
And
this is governed by the laws of. This is the reason. For example, you have also you don't need to have collisions. You don't need to construct a collider. You have collisions by particle coming out of with a solar wind hitting the Earth, and you have similar collision as you record. Only you will never record enough of them to find. But the first elementary particle, as a matter of fact, were observed in such collisions. So these cosmic rays were first observed by Victor Hess, an Austrian physicist actually, but later, for example, positrons.
When was that recorded?
That was already in the 19th century. But later on, for example, one of the first particles which was found by such collisions in cosmic rays were positrons, which were discovered by Anderson, I think, around the beginning of last century.
All right.
So, and then people were doing a lot of observation with these cosmic rays, but then after the Second World War, the accelerator technology was developed, and this led to a breakthrough in that science, because suddenly you could generate such collisions and you could find these rare events where some special particles were produced.
Because those collisions don't happen outside of...
No, they happen, but you will never be... Nobody is there to look at them.
But the particles go so fast as certain other places in the universe? I mean, it's nearly the speed of light. That's what I understood, right?
Yes, but you will have lots of this. You will have any collision like that happening when cosmic rays hit the Earth. The only problem is we cannot lift the Atlas detector to be there when this collision is taking place. While in the Atlas detector we have collisions at a very well-defined point, which is only few hundred nanometers big. So it's a very, we know really the place.
That's where it happens.
Yes,
that's where they cross.
And there are millions, where the beams are crossing, and there are millions of these collisions will take place. This doesn't mean if we would be able to move the Atlas detector up to the atmosphere where the cosmic rays are hitting the Earth, and we would be just in time there to record these events, we would observe the same. Only it's definitely not a practical proposal to do it in praxis.
All right, so there you put it just in a few hundred nanometers, and the 27 kilometers just meet there only.
Yes, yes.
All right.
So this is the fact that we observe so many in a well-defined place allows us to do this measurement.
All right.
While and the events which we are looking now require high energy and they are rare. So this is one of the interesting aspects of physics which is not well understood, is that, for example, we have three families of particles, and what we see around us is basically made by protons, neutrons, and electrons, which is just one family. We don't really understand why there are other. So when these other particles were first discovered in cosmic rays, so the first one they called strange particles, because it was strange that there was another particle, because one was thinking you have protons, neutrons, as far as one was understanding it at that time, and we have electrons, and they form our world, and that's it. But suddenly they were discovering strange quarks, strange particles, and they were not really understood where they're coming from. Then there was a prediction that there might be a further kind of particle, and they were calling them charm, because they were recreating the symmetry. Charm particles. So they were the first were strange because it was very strange. Then when there was the so-called Jim mechanism, which carries the name of one of the former Director Generals of CERN, Majani, who was Director General of CERN some years ago, and because they were predicting a symmetry, and they found a partner particle to the strange quark, the charms. Later they found even more particles, the so-called bottom particles, and then only a few years ago, the top particle was found, which it was complementing again. But we have three of these.
Is that the Higgs?
No, it's not the Higgs. It's not. We are talking. These are quarks. The Higgs is even more mysterious. So these are the basic. But these families, there are three families, and we are very sure that there are these three families. But we don't really know why there are three families, because all the matter which we observe is just made by one family.
All right. So this is. Okay, so this is like a huge experiment.
This is one of the things which we want to understand doing these experiments.
And so all the physicists in the world are fascinated. I mean, they like this place. It's great.
Particularly high energy physicists. I mean,
Yeah.
there are many disciplines in physics,
Yeah.
but for high energy physics, it's generally interesting for any physicist. But there are many disciplines in physics, so there are people.
Yeah.
One problem of this current generation of experiments is that these experiments got so huge. So we have huge collaboration with thousands of physicists. We have a preparation times of 10 years.
Yeah.
This is not everybody is happy with such an environment. There are other experiments in other fields of physics
Yeah.
where you have much smaller collaboration. You have more. You don't have so long preparation phases.
Long times.
It is not super appealing. Not always appealing. For example, if you do a PhD study and you start, well, maybe now when you start you will have a very interesting time. But when you were starting a few years ago,
Yeah.
you are just in the preparation phase. You will have finished your PhD even before the experiment has started.
All right.
So this it poses new challenges to what people can do in their thesis when you have experiments which go over 10, 20 years.
Could you just talk a little bit what you were doing before you came here, and so how long time you've been here?
15 years.
15 years.
Yes.
In CERN.
Yes.
You live in Geneva?
Yes.
All right.
Well, I live in Ferney-Voltaire, which is a
Yeah.
suburb. So I studied physics, and then I was doing a bit computer science, but at university, and I came to CERN about 15 years ago. I was working for 5 years for the Vienna Institute, and since that time I'm working in various in Ferney-Voltaire, which is a
Yeah.
suburb. So I studied physics, and then I was doing a bit computer science, but at university, and I came to CERN about 15 years ago. I was working for 5 years for the Vienna Institute, and since that time I'm working in various functions for CERN.
All right.
And right now I'm working in the grid.
All right.
But I was working before as an experimental physicist in one of the large lab experiments.
Before in the lab, yeah,
In
they
the
had
lab area, in the lab area, yes.
and there you were showing the 20 gigabyte tapes. That was the time.
Exactly, this was that time, yes.
Yeah.
So it was...
And how fast were the processors?
The
Each of them?
processors were very... Well, at that time, computing has changed dramatically
Oh yeah,
over that
you
time.
said there was a supercomputer.
Yeah, there were supercomputers, but earlier, at the time when I arrived, the things which we really would like to have were workstation in the offices.
Right.
And these workstations were costing something like 20,000 Swiss francs, and it was difficult for people to provide workstations to people to work at. And at that time one had like the things which we saw we saw these terminal downs. We had these terminals, they were public terminals rooms where people were coming and were not only sharing computing resources but were sharing the keyboard.
The keyboard.
But so this has evolved.
Yeah,
quite
now it seems
dramatically.
the control room, he said you just log in and then you have your whole thing that shows up.
Yes.
You don't need to go to the same computer all the time.
Yes. So this is all, many things got easier today. But at the time when I was coming here, it was clearly not like that. It was a big thing when I got my first terminal on the table where I could work myself before I had to go to public terminal rooms to use in the infrastructure.
All right. Do you have access to some of the CERN from at home, or you have to come here to the facility?
No one can basically access everything from home.
From home. Any internet connection can. You just need the software somehow.
Well,
it has to be secure.
Yes,
all that.
it has to. Yes. So, but basically, you can connect to basically everything from home. But you can have today. You have things like you can have virtual private networks. I can have a virtual private. I can establish a virtual private network from home to CERN, and then my PC at home is connected like a computer at CERN, except from the speed point of view.
The bit rate, all that. Yeah.
Yes, but on the other hand, this all got much better because today you can do even work from home. I mean, you have DSL is offering you much. It's very different from times there were times when people when things were going over the telephone line, and this was evidently not so nice as today.
So is it maybe easier to travel with the tapes and drop the tapes with the airplane or something?
For some time, data was being transported, for example,
but there was no grid,
to Lyon,
maybe.
From Lyon.
Lyon,
in Lyon, where we have other large farm in the times of Delphi, and we had a little car which was going between Cern and Lyon every week, and which was transporting the tape.
Oh yeah, that was the time. Yeah.
So this was slightly different than today.
All right. So are you very, very busy every day? Because the experiments are coming closer. Are you being more and more busy, or not especially? Everything was planned fine, or is a deadline coming so close that you have to work more?
That's typically people are the real thing which is making. So what we currently don't have is that we don't have round of the clock operation of the experiment.
Yeah.
So I was working before in round. We are still in the preparation phase.
Yeah.
So these days, in these years when the experiment is not yet running, you don't need to spend your weekends at CERN.
Not yet.
Not so much. Well, you can if there's some reason people are doing that, but typically when experiments are running, you have constantly people around on shift, and so this right now you don't have.
Usually now people go home at night and.
Typically, there is not. Well, there are still people who work a lot, but it's not. You cannot compare the situation when the experiment is running. When you have people, so just to operate Atlas, we will have a number of people on shift in the experiments in the institute, which are all checking
24 hours,
24 hours around the clock. Yes.
So it will change soon. A few months.
This will change soon. Yes. Yes, clearly.
Yeah.
I mean the question, but as the things are quite specialized today, it will hit various groups of people at various times. Yeah. The first one which will be hit will be the one who have to get the data from the detector itself outside to the to the upper floor of the grid will be hit a bit later, because in the first weeks the data will not come out at that rate.
Do you have to work a lot on Linux yourself, or?
Basically all Linux, all physics computing is done on Linux at CERN.
All right. So you specifically Linux expert, or?
To some extent, yes.
Yeah.
To some extent, yes. I use, as you were seeing, I use Windows for my laptop. But this is as a laptop. Typically, Windows works nice. And anyway, you have to make presentation, and
PowerPoint is not so good on Linux. Maybe
is a matter of taste, but what you do. But typically, most of presentations are done with PowerPoint.
All right.
These days, it's also available because we have site license. We have a site license with Microsoft. Right. So there is
Microsoft is not angry you're not using Windows on the grid.
The EGE project had the project leader or the director of the EGE project during the first years was hired by Microsoft to promote scientific computing on Windows.
Oh yeah.
Yes.
EGE.
But so this European project. But if apart from that, we are not good customers.
Apart from that, but now he's not the boss anymore.
No. He's been hired by Microsoft, so there's a new boss. But we are not good customers. We are not even good customers in the Linux area, because we are repackaging Red Hat Enterprise Linux into scientific Linux, which is exactly the same thing, but recompiled by us, so we don't need to pay to Red Hat.
Is it free license?
Linux is free and GPL, but when you want to use Red Hat Enterprise Linux, you typically have to pay a maintenance fee, which is and you get some premium support by Red Hat.
Is Red Hat doing most of it?
Yes, but the point is, you are not allowed to. So Red Hat Enterprise Linux, you have to pay when you want to use it. And for such an infrastructure, you need to have this enterprise version of the software. You cannot do it because it's not stable enough. I mean,
Right.
we cannot reinstall our computers every 6 months.
You cannot update Linux.
Yes, but I mean, we have applications which build on top of that. So this has to be done in computing centers. This has a much slower. It's not like we have to
Windows
certify.
update, yeah.
We have to certify new releases that all our applications, which we depend on, are working. So this takes much longer. So we have to use these enterprise versions. But for this enterprise version, you have to pay. But as Linux is is free, everybody is free to recompile it. So we are recompiling our own version of Red Hat Enterprise Linux. So we are not very good customers for.
Red Hat.
Don't pay Red Hat for the Linux which we are using.
All right.
But
Unless
basically the discussion with Red Hat, we wanted to use, but the discussion with as we have these large grid sites, and basically we don't want to pay for 1,000 computers which run,
the same.
which are worker nodes.
You need a special
without grid.
price.
We need a special price, and Red Hat and CERN were not coming to a good conclusion.
Oh, okay. That's too bad for Red Hat.
Well, not really, because they have a price for commercial. I mean, we can do it because we are not a nuclear reactor or a bank or whatever which collapses. Red Hat wants to which collapses when their Linux is broken. Imagine, in the worst case, the physicists have to work harder because the computers are down for one day. It's not that we lose a lot of business because of that.
Yeah.
If you are a company, you are in a completely different situation. You need different kind of support from these companies. And
So
Red Hat is aiming for these customers, not really for us.
not really for you, but they still maybe have some people working with you.
Typically, not really.
Just
We
to
have
check
our
if there's business opportunities. Maybe there are still.
Not that I'm aware of. Not that I'm aware of. But they are. So this is a bit. But I think
Maybe Intel people are working with you, I guess.
We have some contact with company people. We have here. We have some of the hardware there is sponsored by companies where we have some contracts for collaboration.
All right. Okay. But thanks a lot.
Okay. You're welcome.